Hello everyone, this is Nash. Today we're going to be talking about the Lagrangian Mechanics. Just before we start, in addition to the Lagrangian Mechanics, what else have we learned about mechanics? That will be the Newtonian Mechanics. So lots of people might be wondering, why can't I just solve problems simply by Newtonian Mechanics? It is simply because if you're dealing with rather simple problems, that is fine for Newtonian Mechanics. But if you are dealing with complex system with multiple forces acting on it, then there are still some limits about Newtonian Mechanics. First, what about there are too many forces? And some of them are even more mysterious, just like it is not a fixed constant, it is a function. It's a function of time, it is a function of position. Then how would you get the equation of motion? Directly by analyzing the forces. So there are still some limits for Newtonian Mechanics. So that is why we need to learn Lagrangian Mechanics. First, what is Lagrangian? Lagrangian heavily revolves around the central quantity. It revolves around the central quantity called L, a capital letter L. But I prefer writing it in a more curly handwritten style because it's just more beautiful for me, more elegant for me. So this is Lagrangian, defined as a capital letter L, Lagrangian, and the Lagrangian is defined as T minus V. This is the Lagrangian. And the T means the kinetic energy, and V means the potential energy. Okay, so write down the L, the capital letter L is basically the Lagrangian. It's defined as a capital letter L, and the T is kinetic energy. And some people might like to use K for kinetic energy or Ke for kinetic energy. This is trivial, just like personal habit. You can use whatever symbol you like, but here I use T for kinetic energy. And what is V? V means the potential energy. Potential energy. Of course, some people like to use U or PE for potential energy, but right here I use V for potential energy. If we want to apply the Lagrangian mechanics, the first most important part is about finding the Lagrangian of the whole system. And what is more important, you don't need to deal with the force. No matter how complex and how multiple forces are now acting on your body, are now acting on your system, just forget about it. Go straight to the energy and stick them to this definition, Lagrangian, which is T minus V. Kinetic energy minus the potential energy. And you know what, personally, I don't think the Lagrangian does present anything physical. It doesn't present anything physical. What is physical? Like, how about T plus V? The kinetic energy plus the potential energy, which is the Hamiltonian. That might be more meaningful for the T minus V, because T plus V is the total mechanical energy of the system. So at the beginning, you will not feel anything physical simply by the form of Lagrangian. The Lagrangian doesn't present anything physical. So basically, it's not a physically useful quantity. It's more mathematically useful quantity. Why? Because this is the first step. If we want to apply the Lagrangian mechanics, finding the Lagrangian of the system is simply just the first step. And what would be the second step is that you need to plug it in to a so-called famous Euler-Lagrange equation. The Euler-Lagrange equation is like this. The ddt and partial derivative of Lagrangian with respect to q dot, and which will be equal to the partial L with respect to q. This is the Euler-Lagrange equation. In this video, the main goal is about teaching you when is the right timing to apply the Lagrangian mechanics instead of the Newtonian mechanics, and how to solve the problem step by step by using the Lagrangian mechanics. And some people might be wondering, what are those advantages of applying the Lagrangian mechanics? And what will happen once if I plug it in the Lagrangian to this Euler Lagrange equation? What might be happen? What would just pop up? I'll discuss it later. But just before I share a rather simple problems, there's one thing that needs to be mentioned. This type of Lagrangian we are going to be discussing right here is based on classical mechanics. So something like the relativistic or quantum mechanical situation will not be discussed right here. Okay, so this type of Lagrangian mechanics is based on classical mechanics. Okay, so something like relativistic or quantum mechanical situation will not be discussed right here. So in order to realize how should we apply this Lagrangian mechanics step by step, I need to give you an example. One of my favorite rather simple problems, that is a block of mass attached to a spring and doing the simple harmonic motion along the x direction on a frictionless horizontal plane. Let me draw that picture for you. Okay, this is a block of mass m. It is now attached to a spring and doing the simple harmonic motion on a frictionless horizontal plane. And what is more, I want to make it more simple, much more simpler. So let's just don't worry about the mass of the spring. It's an ideal situation. The only thing that you need to care about is the mass, the block of mass, and is now attached to a spring. And once, if your spring is nor extended or neither compressed, it is at its natural position, and the natural position is also called equilibrium point. So let's say this is the equilibrium point. Equilibrium point. This is the natural position. So the position of the block of mass is defined as is denoted as a vector x, like this. The position of the block of mass is defined as a vector x, So secondly, how do we define the velocity? The velocity of the block of mass. Because the first step about applying the Lagrangian mechanics is to find out the Lagrangian, and the first symbol is the kinetic energy. And the kinetic energy is 1/2 mv squared. So I need to find out the velocity. The velocity is an indication. It indicates that how fast your object is now moving, or the distance your object moved per time. So the v is basically dx by dt, the derivative of the position with respect to time t. But right here, I want to change the symbol because the dx by dt is complicated. I want to make it simpler. Because later I will plug this Lagrangian to our Euler Lagrange equation, and you might be wondering, what does the q mean? The q is generalized coordinates. It could be x, it could be y, or it doesn't have to be translational. It can also be rotational, like a phi or a theta. So the q right here is generalized coordinates. And since my block of mass is now doing the simple harmonic motion along the x direction, so later all these Lagrangian, I need to differentiate this with respect to x and x dot. And what is x dot? I'll explain right here. The x dot is basically the velocity. If I want to make the dx by dt simpler, I just need to write down the x and put a dot right on the top of the position. This is the velocity. The velocity is x dot, and that will be more convenient when I plug in the Lagrangian to this Euler Lagrange equation. So the first step about applying Lagrangian mechanics is finding the Lagrangian, right? So the step one is I try to find out the Lagrangian, and the Lagrangian is T minus V. First is about the kinetic energy, and the kinetic energy is 1/2 m times v squared. But now I replaced the v simply by the x dot, so that will be the x dot squared minus the potential energy. The potential energy is stored in the spring, and is 1/2 times k times x squared. What is x? The x could be extension or compression. Could be compression or extension. So that's how you store the energy in a spring. Okay, so now I have derived the Lagrangian of the system. And there's one thing that needs to be mentioned. I don't care about the force. I didn't deal with any force acting on the block of mass. I just go straight to the energy, and later I will stick them. This is your kinetic energy T, and this is your potential energy V. I will stick them to this definition, Lagrangian, and I will plug that in to the Euler Lagrange equation. That will be my second step, and something amazing will just pop up, and let's see what would that be. So the second step is you plug in your Lagrangian to this Euler Lagrange equation. Because this might be your first time to learn Lagrangian mechanics, I'll make it slower in order to have a better understand. So this is ddt, you write it down, ddt, and times the partial L with respect to q dot, and the q is now x because it's now moving along the x direction. So that will be partial Lagrangian. Okay, you put it down, Lagrangian. In order to make it cleaner, so I'll not just write all this term down. I'll just use Lagrangian right here, because the Lagrangian is right here, the 1/2 times mass and times the x dot squared minus 1/2 kx squared. So this is your Lagrangian. I'll plug that in, okay? And which is equal to the partial derivative of Lagrangian. This is x dot, don't forget, with respect to x. The x dot is, don't forget, the x dot is right now the dx by dt. It is velocity. So now I can do the partial derivative of the Lagrangian. When you're doing the partial derivative, just remember, if we're doing the Lagrangian, the partial derivative of Lagrangian with respect to x dot, then only the x dot will act like a variable. And for the x, although they both look similar, but basically they're different quantities. The x is compression or extension or position is totally different from the x dot, and the x dot means the velocity. How fast your object is now moving, the distance you moved per time. So it's totally two different quantities. So if we want to do the partial derivative with respect to the x dot, the x should be regarded as a constant. So this term, if you differentiate this term with respect to the x dot, that will be simply 0. So the only thing that you need to differentiate it will be the 1/2 mass times the x dot squared. Okay, so let's keep going. The ddt. Now the potential energy term will simply be 0, and the x dot, you move the 2 down and times the 1/2, and that will be 1. So the partial L with respect to the x dot will be mass times the x dot, which will be equal to, okay, now you want to do the partial derivative of the Lagrangian with respect to the x. So only the x should be regarded as the variable, and the x dot is totally different quantity. So the derivative of this kinetic energy term with respect to x will be simply 0. So the rest part on the right hand side will be k times x, and don't forget the minus. And just pay attention to this. Now the mass is a constant, so the x dot is the variable, and you want to do the derivative of the x dot, which is the velocity, one more time with respect to time t. So that means you do the derivative with respect to time 2 times. If it is 2 times, you just need to put double dots on the top of the x. So you can imagine the x double dot is just like the derivative of the x dot with respect to time t again. So you need to put double dot on the x dot on the x. So the x double dot is basically the acceleration. Okay, acceleration. So I can keep writing it as the mass times x double dot, and the x double dot is just the acceleration, and that will be minus kx. As some of you might have discovered, the result is simply the equation of motion. Yes, the equation of motion. This is the most charming part for applying Lagrangian mechanics, because start from the beginning, I don't deal with any force acting on the body. I don't deal with the force acting on the body. I just go straight to the energy and find out the Lagrangian and plug that into the Euler Lagrangian equation and do a little bit calculus, and the equation of motion just pops up. No dealing with forces. And some of you might be wondering again. You say, hey Nash, I can get this equation of motion done so quickly, instantly, simply by applying the Newtonian mechanics, because for Newton tells you that if you apply Newton's second law, the net force is equal to the sum. The net force is equal to the sum of all the forces. And now, along the x direction, the spring force is the only force acting on the block of mass. The spring force is the only force acting on your body. So I can directly write down the equation of motion that the mass times the acceleration, which is the x double dot, is equal to the sum of all the forces, and the spring force is the only force. Now, and for this situation, the spring force is the only force. So of course you can write down the equation of motion so quickly. So what should we learn? What should we learn in Lagrangian mechanics if I can solve this problem instantly and quickly simply by Newtonian mechanics? If this could be done so quickly by Newtonian mechanics, and what should we learn Lagrangian mechanics? This is a good question. Think about it. If you're dealing with rather complicated problems, can it be easily done by Newtonian mechanics? If the system is complex, it's a complex enough system. There are multiple forces acting on your body, more than your imagination, and some of the forces are even mysterious. In other words, some of the forces are not a fixed constant. It's a variable. It is a function. It's a function of time. It is a function of position, and there is no way for you to get them done directly by observing by sticking them to the net force, because Newton's second law tells you that the net force is equal to the sum of all the forces. So you need to find all the forces with exact value and plug that in to this equation of motion. But how could you complete this equation of motion if you don't know what the force might be? Because it could be a function and you don't know what the function might be. When you are facing these such rather complicated problems, then maybe it is the right timing for you to consider about the Lagrangian mechanics, because for Lagrangian mechanics, you don't need to deal with all the forces, no matter how complex that it is. You just go straight to the energy and find out the kinetic energy and potential energy, and the T minus V is defined as the Lagrangian. Although it doesn't present anything physical, I'd say it's not physically useful quantity, it's mathematically useful quantity. But however, when you plug that into the Euler-Lagrange equation, and the equation of motion just pops up. This is the most charming part if you're solving rather complicated problems, and that is the right timing for you to apply the Lagrangian mechanics. In other words, the more complex your system is, the more powerful and clever that your Lagrangian mechanics will be. Okay, so what are those the so-called complicated problems? Let me give you one example. It is still a mass attached to a spring. You say, this is easy, Nash, this is a rather easy problem. However, how about it is just now it is attached by another single pendulum? Is it complicated enough? The advantage, there's another advantage for applying Lagrangian mechanics is that the Q is generalized to coordinates, so it doesn't have to be translational, it doesn't have to be X, it doesn't have to be Y. If it is now doing two-dimensional motion, I can not only just get the equation of motion along the X direction, but also along the Y direction. And what is more, I can even use the Lagrangian mechanics to get the equation of motion of a single pendulum, because the Q can be replaced by rotational coordinates like the theta. So if it is now combined, it can still be solved by Lagrangian mechanics, because the Q could be generalized to coordinates, not just for X, not just for Y, but also for phi or theta. If it is not complicated enough for you, let's just attach by another single pendulum, and let's make it a double pendulum. It is now attached to a mass, and the mass is attached to a spring. Is it complicated enough? I think it's complicated enough for me. Okay, if you are dealing with such complicated problems, then you might feel the Lagrangian mechanics is clever and powerful. So the advantages of Lagrangian, I'll list two advantages of applying Lagrangian mechanics. The first is it gives equation of motion directly, without dealing with force, only the energy. Just go straight to the energy, and you can get the equation of motion. It gives equation of motion without dealing with force. Or you can say without dealing with multiple forces. No matter how complex your system is, with multiple forces acting on it, ignore them. You don't have to handle all those forces. Just go straight to the energy and find out the Lagrangian and plug that into the Euler-Lagrange equation. Then you can get the equation of motion. No matter how complex your system is, no matter how many forces are now acting on your body, you don't need to care about that, because the Lagrangian mechanics can give you the equation of motion without dealing with any force. And of course, if the motion is complex, is complex. The Q is generalized coordinates. It can help you to solve the equation of motion simultaneously along the x direction, y direction, or rotational coordinates like the phi or theta. So it's powerful. It's powerful for you. Okay. So the second advantage is it's good. It's good for dealing with multiple coordinates. So these are the two advantages. Personally, I think it's the biggest two advantages for applying the Lagrangian mechanics. It can help you to solve rather complicated problems without dealing with all those complex systems, all those complicated forces acting on your body. And secondly, you can get the equation of motion not just along the x direction, not just for translational coordinates, but also for rotational coordinates. And during all the process, no need to handle the force. Just go straight, try to find out the kinetic energy and potential energy, and the T minus V is defined as L. It's mathematically useful quantity, not physically useful quantity, I know, but it doesn't matter. Just plug that into the Euler Lagrangian equation and be patient enough to the partial derivative of the Lagrangian with respect to position, with respect to velocity, and with respect to time. Then the equation of motion will just pop up, surprisingly. So even though the Lagrangian mechanics is clever and powerful, it is still complicated to solve such problem. So I'll give another middle-level problems in order to help you solve the problem step by step while using the Lagrangian mechanics. First, let me clean this blackboard for you first. Hello everyone, this is Nash. The problem I'm going to show you is a disc, a rolling disc attached to a spring without slipping. Since it is now doing the motion without slipping, so you can guess the spring force is no longer the only force. However, there's another force. If I want to roll, there must be a friction. Yeah, there must be a friction between the rolling disc and the horizontal plane. So the plane is now no longer frictionless. So in order to solve this problem, in order to make it feel how clever the Lagrangian mechanics can be, I first to try to solve this problem simply by Newtonian mechanics. For Newtonian mechanics, Newton's second law, it tells you that the net force is equal to the sum of all the forces, and the net force is equal to mass times the acceleration, and the acceleration is now represented as the x double dot and is equal to the sum of all the forces. And now, in addition to the friction force minus kx, in addition to the friction force, you also need to consider about the friction. The spring force is no longer the only force. And some people might be curious, why should I put a minus in front of it? Because the direction of a friction force is different. It's different with the position of your disk. For example, if it is now rolling from the equilibrium point to the end point on the right-hand side, I say, what is the equilibrium point? The equilibrium point is at a natural position when your spring is neither extended nor compressed. It is at its most comfortable position, its natural position, and that point is equilibrium point. It's equilibrium point, and that is how we define the position of your object. The position is now pointing to the right, but your friction is now pointing to the left. So that is why I should put a minus in front of the kx, because your spring force and the position are pointing to opposite direction. So my first question is, which direction is the friction now pointing to? Is the friction now pointing to the right? Or is it now pointing to the left? That is a question. Not that easy to answer, right? And some of the physics students, they might say, it's not that hard. I'm a physics student. I get a good sense of dealing with all the forces. They say, hey Nash, look, since your disk is now rolling, it's now moving from the equilibrium point to the end point on the right hand side. It's now rolling clockwise, and however, it is now slowing down. So I can guess if friction should generate a torque in order to slow it down. So I can guess the direction of the friction is now pointing to the right. Nice try. Maybe you can answer the first question. The first question is, what is the direction of your friction? Which direction is your friction now pointing to? Maybe you can guess the direction of the friction. But what about question 2? My question number 2 is, what is the value? What is the value of your friction? Is it a constant? Is it a constant? Or is it a function of time, a function of x? You don't know. So that is why it is hard to make this question, to get this question done simply by Newtonian mechanics. Since you don't know, you may know the direction, but you don't know the size of the friction. You don't know the size of the friction. So that is why it's hard to apply the Newtonian mechanics to solve the problem. So maybe it's the right timing for you to consider about the Lagrangian mechanics. Since Newtonian mechanics, there are some limits for it. Once, if you don't know the force, maybe you get a good sense of dealing all the forces, no matter how complex your system is, no matter how multiple the forces are. Once, if some of the forces are quite mysterious, you don't know the size, you don't know the direction, then it's hard to get the equation of motion simply by the Newtonian mechanics. And maybe it's the right timing for you to apply the Lagrangian mechanics, since there are still some limits for Newtonian mechanics. So let's just learn how to solve the problem step by step while using the Lagrangian mechanics. For the Lagrangian mechanics, the step 1 is you try to find out the Lagrangian of the system without dealing with the force. You just go straight to the energy, find out the kinetic energy and the potential energy. And the Lagrangian L, defined as the capital letter L, is defined as T minus V. And the T means the kinetic energy and V means the potential energy. Personally, I don't think it presents anything physical. I say it is not a physically useful quantity, it is mathematically useful quantity, because you need to combine the Lagrangian with the Euler Lagrangian equation, and the equation of motion will just pop up. Okay, so what is the kinetic energy of the system? The kinetic energy is 1/2 mv squared, and the velocity v is now expressed by x dot. So the Lagrangian is equal to kinetic energy minus the potential energy, and that will be equal to 1/2 mass times x dot squared minus the potential energy. You think it would be that easy? No, because your disk is now rolling. So in addition to translational energy, there is one more energy that you need to consider, that is the rotational energy. So the kinetic energy will not just be expressed simply by the translational energy. This is 1/2 mv squared. This is translational energy, translational kinetic energy. And you also need to consider about the rotational kinetic energy, rotational energy. So the rotational energy is 1/2 times the moment of inertia and times the omega squared. Okay, that is the total kinetic energy of the rolling disk. And this is for translational energy, and the right hand side is rotational energy. That will be the total kinetic energy. Okay, and the omega is the angular frequency of the angular velocity, how fast you are now changing the angular displacement, or simply you can call it the angle, how fast you are now changing your angle, how fast you are now changing the angular displacement. This is the kinetic energy, and minus the potential energy. The potential energy is still stored in the spring, that is 1/2 k times the x squared. Okay, the Lagrangian is done. And this is a roll. I say this is a disk. This is a rolling disk. So the moment of inertia, I is equal to 1/2. Let's say this is a mass. 1/2 mass times the radius squared. 1/2 mr squared. Okay, this is the moment of inertia. Okay, now I need to make the Lagrangian simpler. I need to make it simpler. So I need to find out the relationship between the omega and the velocity. The omega and the velocity. Okay, the velocity v is now expressed by x dot. Okay, if you're not quite used to use the x dot, maybe you can change it back to the velocity temporarily. That's okay. The v is equal to r times omega. Okay, if the radius is capital R. So the omega is v divided by the r, v divided by r. So you can replace the omega by v over r. Okay, let's just plug that in to this moment, to this omega, and the moment of inertia is 1/2 mr squared. You stick them all to your Lagrangian. So let's keep writing down. The Lagrangian is now 1/2 mv squared plus 1/2 times the moment of inertia. The moment of inertia is 1/2 mr squared, and times the omega. The omega is v over r squared. Okay, this is the kinetic energy, the total kinetic energy, and minus the potential energy. The potential energy is 1/2 kx squared. Okay, let's take a look at this Lagrangian. See, the r squared can now be cancelled. Is it okay for you? The r squared can be cancelled, and the Lagrangian is now equal to a 1/2 plus a quarter. That will be 3/4. Okay, 3/4. So the Lagrangian is now equal to 3/4 mv squared minus 1/2 kx squared. Let's check. Is it okay? I think it's okay right now. So far, so good. So this is the Lagrangian of my system, of the rolling disk attached to a spring. This is our Lagrangian. During all the process, I don't need to handle all the forces. I don't need to handle the friction. I don't need to handle the spring force. I just need to go straight to the energy, the total kinetic energy and the potential energy. The kinetic energy is now expressed by two terms. One is the translational energy and the rotational energy. And the potential energy is stored in the spring. For its compression or expression. Okay, this is the step 1 for applying the Lagrangian mechanics. So now I can start to do the step 2. The step 2 is plug your Lagrangian to the Euler Lagrangian equation. The Euler Lagrangian equation is ddt partial L with respect to x dot is equal to partial L with respect to x. Okay, now I want to do the partial derivative of this Lagrangian. If I want to do the derivative of the Lagrangian with respect to x dot, then the x will be constant, is simply constant. So the derivative of this constant term is simply 0. Now you can replace the v. You can replace the v as x dot. This is x dot. Okay, so the partial derivative of the Lagrangian with respect to x dot will look like this. This potential term will be simply 0, and you want to do the derivative of this kinetic energy term. So you can move the 2 down and times the 3/4, and that will be 3 halves. 3 halves. 3 halves and v squared, and the v is x dot. Is it okay? Is it okay? Okay, on the right hand side is partial L with respect to x. So now the x dot will just be regarded as a constant. So the only thing that you need to differentiate is this potential energy term. And don't forget the minus. Don't forget the minus, the negative. So the partial L with respect to x is minus. You move the 2 down times the 1f, and that will be simply 1 is k times the x. And you just do one more time derivative of the x dot. If you want to do it one more time, that will be x double dot. That is the acceleration. So I can get the equation of motion now, because the derivative of all of this term with respect to time t is simply 3 halves m x double dot. That will be equal to minus kx. If I switch it a little bit, and that will be mass times the acceleration is equal to minus 2/3 and times the kx. 2/3 minus 2/3 kx minus 2/3 kx. This is the equation of motion, right? Equation of motion. So I don't need to handle all those complex forces. I just need to find out the energy, the Lagrangian, and plug that into the Euler Lagrangian equation. Then I can get this equation of motion done. And what is more, since the net force is equal to the spring force plus the friction, so the minus 2, the 2/3 kx is composed by minus kx and plus 1/3 kx. What does it mean? The minus kx is the spring force. As I know, there's another force, that is the friction. At the beginning, if I want to solve the problem simply by Newtonian mechanics, there are some limits. because I may know the direction of the friction, but I don't know what size it might be. I don't know the value, I don't know the function. But by using the Lagrangian mechanics, I can know that the friction F, your friction F is just 1/3 kx. It is indeed a function of position. It is indeed a function of position. So that is the most charming, the most attractive part for Lagrangian mechanics, because I can solve something cannot be done simply by Newtonian mechanics. I can not only know the value, the size, the function of your friction, I can also know the direction exactly of the friction. Why? Because the minus kx is now pointing to the left. So if we cancel the minus, it is now a positive 1/3 kx. So I can know the friction is now definitely pointing to the right. It's definitely now pointing to the right. And for friction force is now pointing to the left. So by using the Lagrangian mechanics, I can not only know the direction of the friction, but also the value, the size, the function of your friction. That is amazing. So the more complex your system is, the more clever, more powerful the Lagrangian mechanics will be. And in addition to this, you can switch it a little bit because it will be the mass times x double dot plus plus 3 times mass and 2 times kx, that will be equal to 0. Right? Okay, this is a second order linear differential equation. So I can know that this term, the 2k over 3m, is basically the omega squared. This is the angular frequency. So with this angular frequency, I can also derive the period of time, because the period of time is simply 2 pi divided by the omega. But that is not the main goal right here. I'm telling you that by using the Lagrangian mechanics, it can complete something cannot be done by Newtonian mechanics. And for this, this is a second order linear differential equation. So this rolling disk attached to a spring is basically not doing the simple harmonic motion. So you can use the angular frequency to find out the time for you to complete a circle. That is the period of time. Okay, so in this video, the main goal is showing you that when is the right timing that you can apply the Lagrangian mechanics, and what are those advantages of Lagrangian mechanics, and how to solve the rather complicated problems step by step using the Lagrangian mechanics. Hope you like it. Thanks for watching. This is Nash. Oops. Let me correct some little mistake. I should cancel the m. A little bit nervous. I should cancel the m. So, okay. Now the equation of motion is correct. Check it again. Okay, done. Goodbye.